So last time we discussed partition. So you can partition a activity diagram into different parts performed by different classes, responsible entities. So for this example, no, it's mute. So anyway, so for this example, we had this activity diagram partitioned into two parts. So one is authorized payment, which is performed by the finance department. One is the order processing, performed perhaps by the sales department. So they communicate by the cross-boundary messages. So later, when you implement it, you can imagine having an object representing the finance department and another object representing order processing, and they have a sequence diagram that shows how the messages pass back and forth. So here's another example of a managed section. So the course has a section. So first you create a section and then assign instructor, create web page, and register for section. And eventually it's either offered if there's enough people who register for it, or canceled if there's too few registered students. So you can partition it so that registrar does this create section and cancel section, and student does register for section, and professor does assign instructor, create web page, and if it's offered, then at the end of the semester you assign grades. So you can imagine having a perhaps a sequence diagram. First you have a message from registrar to professor, and professor to student, and student to professor, and so on. So you can activity diagram has a lot of the same information as the sequence diagram. They just add a different way of expressing this flow of activities. So you can draw a sequence diagram from the activity diagram after you've done the partitioning. So here's another example of a activity diagram. So it describes register for a course procedure. So this is the a slightly different example from before, where this one is for describing the internal details of an operation, while the previous ones are describing the high-level workflow. So this is a more of a detail level. So so from the previous paragraph, you can draw this. So essentially, it's a flowchart, check enrollment. If it's open, then you check exclusions, that is exclusive courses. If you take course A, you cannot take course B. And if you does not have any exclusions, that is you haven't taken any courses that's an exclusion of this course, then you check prerequisites. And if you have, if the student has the all the prerequisites credits, then you can register. Or if it doesn't have the prerequisites, then you can check permission from the instructor. So, and you have permission, then you can register. Otherwise, if you do not have permission, then you go to abort. So essentially, this pass is a successful pass from here to here to register, or from here to here and back to here. Another successful pass. All the others are failure paths that go to abort registration. So this is so this activity diagram describes the internal details of register for a course procedure. So this procedure is perhaps defined as an operation in the course class. So this is not concurrent. This is a sequential flow of control. So therefore, you do not do partitioning on this one, because it is done as a single flow, sequential flow. If you do partitioning, you're assigning different parts to different rows, and it implies concurrency. But here, it's the job of a single object that does all these things sequentially. So there's no concurrency. So when to use an activity diagram? So first, to show the procedural flow of control of an operation, that's the example of I just showed, the section object. So actions represent the computation of the operation. You can directly map the activity diagram into C or C++ code that uses if then else and while loops to implement all the flow of control. Another usage is to show workflows and multi-threaded programs. This is at a higher level of abstraction. So you show the steps of a use case, possibly with parallel, that is multi-threaded behavior. So that's the example I showed earlier on the managed section and process order, authorized payment. So each action must be expanded as one or more operations assigned to a specific class. That is, so look at this example. Each one, say, create web page or assign grades. These are high-level activities. So they're actually consist of a series of invocations to operations. For example, this is assign grades is perhaps some operations in the professor class, and register for section is some operations in the student class. So while for this one, this is the internal details of one particular operation. So therefore, activity diagrams can be used for both cases. One is at a low level to show the internal behavior of an operation. One is at a high level to show the workflow. And each action is an invocation of several operations. So questions? So now we move to packages. So this is the analysis workflow. So we discussed analyze use cases and analyze classes, and now we're trying to group classes into packages to better organize the system. So a package looks like this. It's essentially the icon for a folder in Windows, right? it's like a file folder with a little sticky little thing as a label. So it means that it's a collection of related things. So it groups analysis classes for ease of use, maintainability, and reusability. So a package can contain analysis classes and other analysis packages, just like folders can contain files and other folders. 2 or 3 levels of nesting is sufficient. Do not nest too deeply. So criteria for allocating classes to packages. So first, to support a specific business function. So perhaps you have a package for the sales order processing, another package for say finance operations, or to support a specific actor, say all the professor-related classes are grouped into a single package. For example, related by generalization and extent relationships. So if you have a class hierarchy of a base class and some subclasses, then you should put them into a single package. And if you have dependencies between classes like associations, then it's possible to put them into the same class for different classes, depending on how tightly they're related. If they're loosely coupled, then put them into separate packages. But if you have generalization, then always put them into a single package. Encapsulate some system functionality. So the key is if you have encapsulation, then you can have better maintainability and reusability. So goal is to localize changes to the system. So we'll show next that a package can have different parts as private and public. So to minimize if you minimize the public parts, then you minimize the coupling and localize changes. So if you change the private parts of the package, you don't have to affect the other packages. So cohesion and coupling, we want packages to be highly cohesive and loosely coupled. So these 2 criteria also apply to components and modules. So packages, analysis packages, eventually they're likely to be turned into components at design and implementation level. So cohesion is a measure of the number of functionally different things a package has to do. So a package is most cohesive when it does only one thing. So cohesion, you can have a spectrum of levels of cohesion. So one is on the extreme level, you have so-called scatterbrained. That is, you're really having a lot of things in your mind, and you're not focused at all. So on the other extreme is single-minded. That is, you're extremely focused on one thing only. So coincidental. That is, the package does not achieve any definable function. That is, perhaps you just group the packages by line number, for example, or alphabetically. That's coincidental. Logical. That is, the package contains similar but slightly different functions. Temporal, when the package contains various functions that happens to be executed at the same time. during execution. And procedural is when the package functions must be executed in a pre-specified order to form a whole complete procedure. And communicational is when all package functions operate on the same data stream or data structure. So the data stream flows through all the package functions. And eventually the highest, the best one, the green one, is the functional. That is, the package has one and only one identifiable function. So these details, you don't have to really memorize all the details. All you need to keep in mind is that it's good to be cohesive, and the spectrum from the least cohesive to the most cohesive. So coupling describes a measure of the number and types of dependencies a package has with other packages. So lowest coupling when it has minimal dependencies with other packages. So you have a spectrum of coupling. So these three here are green, which means that they're good. No direct coupling. The packages are not related. This is not realistic. Packages often must communicate with other packages. Perhaps the two packages that are connected indirectly, but eventually they will be connected. So, or data that is they pass only simple data as a parameter list. This is the best one. So and up to the highest coupling is when you have content coupling. That is, one package makes use of the data or control information maintained within another package. So this is when you directly reach over and grab the data or control information, which means that you're making if then else decisions based on some information in some other package. Without this, you do not have any encapsulation. You're just treating each other's data as a common global data space. So this is very bad because this introduces high coupling. Whenever you change anything in one package, you must simultaneously modify the other packages that are accessing this data. So, but for, say, the data-based coupling, where the packages only pass parameter list as defined in the perhaps operation signature, then you can feel free to modify a package as long as you keep the interface constant. Or even if you change the interface, you only need to modify small parts of the other package. So there's a trade-off between cohesion and coupling. So say if you have a very fine-grained grouping of classes into packages, then you're likely to have very high cohesion because each package does only one or a few things. But you're likely to have high coupling because it's very fine-grained. So imagine a graph. You're cutting the graph, right, into small pieces. Then you're likely to have many edges that cross the package boundaries. But if you have a coarse-grained grouping of classes into packages, then perhaps you can group a lot more classes into a single package, and the coupling between packages can be reduced. If you cut the graph into a smaller number of components, each one having a large number of classes. But that may result in low cohesion because each package contains many things and does many things. So that's a trade-off. You should make your decision to try to, here's a heuristic, 7 plus minus 2 heuristic, which means that you should try to have a package to be coupled to no more than 5 to 9 other packages. So this seems to be a reasonable degree of coupling that is acceptable, while at the same time maintain high cohesion. Of course, it's just a heuristic. The reason we have the heuristic is because the human mind has the limit of perhaps understanding 5 to 9 pieces of information at the same time. Just some psychological studies. So it's just for the developers to understand the interactions among the packages. If you have more than 9 interactions to consider at the same time, it may be difficult. So, of course, feel free to have different numbers for your specific application if you feel it's appropriate. So a namespace, so a package defines a encapsulated namespace. In C++, you even have the keyword namespace. That is, if you declare a namespace, then all element names in the package must be unique. Element meaning classes and other packages. So to refer to an element in a different namespace, you must specify the name of the element plus the path name to get to it. So package 1 : package 2 : class name. So I think in Java or C++ you have a similar syntax of namespace 1 : namespace 2 : etc. So this means that this class is contained within package 2, which is in turn contained within package 1. So you refer to it from the hierarchical path name. So a dependency exists between packages if changes in one package may cause changes to the other, or if one package is needed by the other to carry out its functionality. So this means that package A is dependent on package B, but not vice versa. So that is, package A can make procedure calls or send messages to package B, but package B cannot directly communicate with package A. So by the way, in the first part, all element names in the package must be unique, but between different packages you can have the same name. So why? Because between different packages you have the path name. So as long as the package names are different, even if you have the same class name, it's fine. But within the same package, you have the same path. Therefore, you must have different class names. So, coming back to dependencies, so there are several types of dependencies. One is a use, where a client uses the element in the supplier in some way. So this is a general form of dependency. That is, all the others are really some special use dependencies. So import, if a client package imports a supplier package, then the namespace of the supplier is added to the namespace of the client. So anything any class name defined within the supplier package can now be used in the client package without prefixing the supplier package name. If you do an import, I think in Java you have the same rule. If you say Java import another Java file, then you can use that all the names within the other Java file. So elements in the client can access all public elements in the supplier. Again, elements referring to classes or sub-packages. So a client access a supplier. So access, it means that it can access the public elements, but namespaces are not merged. That is, the client must use path names. Say with the path name supplier : class name. So if you use import, then you must make sure that there's no name conflicts. If you have the same class name in the client and server packages, then you cannot import unless you change the name. But access is okay because you keep the whole path name of the supplier elements. Or trace represents a historical development. For example, a design model has a trace dependency to the analysis model. That is, here's historical dependency because you do the analysis model, design it first, and then from that you design your design model, which we'll discuss in the next chapter. So this is development of one element, a more abstract element, perhaps a abstract professor class in an analysis model, which is turned into a more refined, more developed professor class with more detailed definitions of the attributes and operations. So access and import are not transitive. The transitive means that if A accesses B and B accesses C, then A accesses C. That's transitive. But in this case, they're not transitive. That is, if you have A access B and B imports or accesses C, then A does not really access C. So this is different from the more usual transitive relationships. So consider navigability. If you have the dependency arrow pointing in this direction, it means that you can navigate from package A to package B, but not vice versa. So this is similar to dependencies in the class diagram, except these are packages of classes rather than classes. So elements within a package may be public, private, or protected. A public element is visible to other packages. A private element is not visible, and the protected element is only visible to child packages. So again, elements can be a class or a sub-package. So compare this to the attributes and operation visibility within the class. So a public attribute is visible to other classes. A private attribute of a class is not visible to other classes. And the protected attribute of a class is visible to its child, that is its subclasses, forming a inheritance relationship, generalization relationship. But here this is visible to child packages because packages do not inherit. You do not have generalization relationships for packages. You only have containment of parent containing some child packages. So obviously, you should try to minimize the public elements and maximize the private elements to minimize coupling. So if you have everything private, then it's the extreme low coupling, because no one can refer to anything within the package. But that's not realistic, right? So you should try to make a few important kind of interface classes to be public, while keeping most other classes private. So layers and partitions. So recursively dividing packages into smaller and simpler packages leads to a hierarchy of packages and layers. Each layer provides higher level services and uses services of lower level package layers. So it forms a tree with the root as a top level package, and gradually you have lower and lower level packages. So application packages come from decomposing the packages. You have application-specific part, a sub-package that is the part of the system that is not shared by other packages, and application general that is part of the system that is reusable within the business or application domain. So, for example, if you're developing an application for a stock brokerage firm, perhaps you have application general packages as, say, the generic financial transaction software that applies to any financial company without distinction to any specific company, while you have application-specific packages that contain the business logic specific to this one company, say Merrill Lynch, which is not applicable to any other company. So middleware and system software packages are added during design to handle the implementation environment. So middleware is something that sits above the operating system, i.e. the system software is the operating system, Windows or Unix. Middleware sits on top of operating system but below the application. So it acts as the glue, the intermediate layer between the system and application to perform, to simplify application layer. If you don't have middleware, perhaps you need to implement a lot more in the application packages and make the packages very fast. But by pulling out some more common services into middleware, for example, communication between different computer nodes, put them into middleware so you can simplify the application. So here's the ASU example. So you have the use case model. Register can do 4 use cases: maintain student information, professor information, course information, and prepare course catalog. A student can register for courses. A professor can select courses to teach and request enrollment list for a particular course. And finally, time, as we mentioned, time can be an actor if the use case is triggered by time. Prepare billing information and which sends information to the billing system as an actor. So group the use cases into major functional areas and put each one into a package. So now we're going to design 3 different package groupings. So the first one is the most coarse-grained one by grouping the use cases into 2 packages. One is information maintenance performed by the registrar, that is to maintain, to modify, create, delete information regarding student, professor, course, and course catalog. And the other is course registration performed by the student, professor, and time-triggered billing information preparation. So the other, that's the use case view. The other, from the analysis classes point of view, remember we drew this big messy diagram before, and we explicitly mentioned do not draw it yourself. This is just for your information only. So from the each use case is implemented by a collection of analysis classes, and some analysis classes, especially the data-related parts, that is all the entity classes like student, course, section, professor. These are often shared among different use cases, while the other, like boundary classes and control classes, are specific to each use case and not shared among different use cases. So here we pull out registration data as the all the entity classes pertaining to persistent data, while all the control classes and boundary classes related to course registration are grouped into one package, and all the control and boundary classes related to information maintenance are grouped into another package. So here's the grouping by functional area, where you separate data management, that is registration data containing all the entity classes, from actor-related functionality. So information maintenance is related to registrar, actor, and course registration is related to professor students. So because data management is potentially reusable in other applications, which means that all the professor student information, they may be also used in, say, billing system or some other system in the university. So so you put it into an application general layer, and these two are application specific packages in the application specific layer for the course registration system application. But registration data is application general. That is, you can reuse it in some other applications perhaps in the future. So, design 2 of the packages is when you make a finer grained partitioning of. So information maintenance is now developed into people maintenance of maintaining student and professor information, and course maintenance That is all the course information and catalogs. So now the registration data package containing all the entity classes, it's still the same. Course registration package containing all the control and entity control and boundary classes related to course registration. But now the people maintenance contains the boundary and control classes for student and professor, and course maintenance package contains all the course boundary and control classes. Remember, the convention is to have a UI suffix to the class name to represent that it's a boundary class, and a manager suffix to indicate that it's a control class. Of course, it's just a convention. You can use different names if you want. So now application-specific layer has, before we had one package, information maintenance. Now we have two, course maintenance, or more precisely, course information maintenance and people information maintenance. So design 3, now you make a different grouping. So now yellow parts, student UI, course UI, professor UI, student registration UI, and professor UI. So these two professor UIs are different. One is for the registrar to enter or update professor information. One is for the professor to access course information. So these are different boundary classes. The parts in red are the student and professor control classes, and the parts in green are the course control classes. Parts in blue still the same as the entity classes put together, and parts in magenta refers to the control classes related to registration functionality. Notice that the billing system UI, so this is the interface, the boundary class between the billing system and the current system, the registration system. So this is not grouped in the yellow because even though it's a boundary class, it's really very different from the other boundary classes, which are user interfaces. While this billing system UI is really interfacing to a billing external system, so it's not a say later turn into a dialog box like the others. So therefore, we put them into the magenta package. So now we have user interface. So separate the UI from the other functionality. We have UI parentheses human, which means that the billing system interface is not a human interface. So we do not put them into the user interfaces package. And dependencies are course maintenance, course registration, people maintenance are dependent on registration data, and user interfaces are dependent on all the other three. So these dependencies are consistent with the dependencies in the class diagram, in the analysis class diagram. So the difference between this one and the previous grouping is that now you pulled out all the UI classes into a separate package. Therefore, even though the 3 packages here and the 3 here, they look the same, but now they contain less information because all the UI parts are pulled out into user interface package. The reason you want to do that is perhaps for better modularity. Perhaps you have a UI expert who's just focusing on the UI package, so that if you pull them out into a single package, it makes the source code control and maintenance easier. So yet another design is when you partition all the entity classes before we put them into a single package. That is the data, registration data package. Now we put them into divided into course data and people data. That is the professor and student. So now instead of a single data package, we have people data and course data. So now people maintenance only refers to people data. Course maintenance only refers to course data, while course registration refers to both packages. So these dependencies can be inferred from the dependencies in the class diagram. So by tracing these lines here, you can draw the lines in the package diagram. So why do you want to do that? So now you have a fine-grained partitioning. So now if you modify the course data package, you only need to remember to also update the course registration and course maintenance packages. You don't have to worry about the people maintenance package because there's no dependency from people maintenance to a course data. Therefore, while in the previous design, if you modify the data package, then you must worry about all the other packages. So we are at the end of the analysis chapter. So in retrospective, so we discussed use case analysis. So you have a use case with the flow of control that you designed in the requirement specification document, SRS, system requirement specification. Now you need to take that in and design a collection of analysis classes that collaborate to perform the use case, to implement at an abstract level, not really implement, but to design classes, boundary control and entity classes to carry out the use case. So we discussed sequence diagrams to show how each use case is realized by objects and show message sequencing, or activity diagram that show the workflow among objects of a use case, especially concurrency. By partitioning the activity diagram, we show concurrency. So, of course, sequence diagrams are naturally concurrent, right? You have the vertical lines, each one representing a role that an object plays in the sequence diagram. So oftentimes the sequence diagrams and activity diagrams contain more or less similar information. But activity diagrams are typically at a higher level of abstraction, well, to emphasize workflow. And furthermore, activity diagrams do not have to be partitioned. Unlike the sequence diagrams, where you must specify each and every row at the vertical line, activity diagrams can be just showing a workflow without showing who does what. So that's actually a benefit because in the early design stages, you don't have to worry about too much details. You just draw the workflow, and then you leave the decision as to who does what in the future. So typically, you design the activity diagrams first, and then partition it into different rows, and then finally you draw a sequence diagram. So analysis, class analysis, assigns responsibilities to and identifies collaborators of classes. So CRC cards help identify classes, responsibilities, and collaborators. That is the you have a class name on the top, and on the left you identify its responsibilities representing perhaps later turning into operations. On the right you identify the collaborators which are later turn into associations. So for each class you specify its behavior as a state machine diagram to show its response to external events by changing state. So as needed, that is, not every class needs a state machine diagram. Only the classes with significant dynamic behavior needs it to make things more clear. So for many simple classes, perhaps if you draw the state machine diagram, you have one state or two or three states. Perhaps it's not worth it. So activity diagrams can be used to specify the methods. That is, remember, method is the implementation of an operation. It's an interface classifier instance distinction, right? So specify the methods, that is the internal details of an operation. How what does the operation do internally? So that's like a flow chart. So activity diagrams really can be used both ways. One is at this high level use case analysis level, where you're showing the overall high level workflow, and also at the low level in the class analysis part to show the implementation of a particular small operation. So in the first case, you have concurrency, where different parts are carried out by different perhaps objects. While for this use, you don't have concurrency. If you're specifying the method, it's just a flow chart. So package analysis organizes analysis classes into cohesive, loosely coupled units. So cohesion refers to if it does one thing very well and it doesn't do many things at the same time, that's cohesive. Loosely coupled means that it doesn't talk to many other packages. So we have the trade-off relationship. If you have very fine-grained grouping of classes into packages, then you have high cohesion but high coupling. If you have very coarse-grained grouping, then you have low coupling and low cohesion. So you have a trade-off with the 7 plus minus 2 rule of having a package coupled to no more than 5 to 9 other packages. So the analysis model. So this is the artifact that you produce at the end of the analysis stage. Contains use case realizations dash analysis. So this is the collection of control, boundary, and entity classes that realize a specific use case. So dash analysis means that these are abstract analysis classes. Later we'll learn use case realization dash design. Then you have design classes that are more concrete. So localized changes in the use cases. So that is when you update one use case, you only need to update all the analysis classes designed for to realize that particular use case. So analysis classes, their responsibilities, attributes, relationships, and special requirements, localized changes to boundary, entity, and control classes. So analysis classes are very abstract. For example, you can just draw a professor boundary class, put it into the analysis model. Later, it can be turned into perhaps dozens or more dialog boxes and hundreds or more implementation classes. You can change your UI implementation greatly in the later design stage and design and implementation stage. While in the analysis model, you only have a single icon representing the professor interface. So that's what it means to isolate localized changes. So analysis packages and their dependencies to localize changes to business processes, actors' behavior, or closely related use cases. So if you have some use cases that are closely related, then perhaps you want to group them into group their realizations, analysis classes into the same package to reduce coupling between packages. So architectural view of the analysis model, that is the layered view. You have where you have application specific, application general, and middleware and operating system. So in the analysis model, we really only have application specific and application general packages. Later in the design model, we'll show the middleware and OS packages, because in the analysis stage, we shouldn't bring any implementation details into the model at all. We should only be focused on the business logic, on the application functionality. So this is to localize changes to the architecture of the system. So the architecture is the layered structure. So if you change any part of the layer, you only need to update the packages that are dependent on this particular layer. So this is documented in the SAS, System Analysis Specification, as opposed to the previous, we discussed System Requirement Specification, SRS. So okay, that's the end of the analysis chapter. So any questions? We'll move on to design, the next chapter. So the learning objectives are to understand the role of and importance of system design, understand the system analysis and design are intertwined activities. So oftentimes you have a blurred boundary between these two. Oftentimes you are transitioning from the analysis model gradually into a design model by refining parts of it to be a more concrete design models and leaving parts of it as more abstract analysis models, and eventually, gradually, one by one, you turn it into the design model. So we will discuss architectural styles and design patterns for realizing system design goals. That is, these are best practice experiences summarized from many years of industry practice. Know the major activities that take place during system design. So the system design adapts the analysis model logical structure to the implementation environment and prepares it for implementation. So it's not implementation yet, but we are bringing in a lot of the platform details like middleware and OS, so that implementation, the implementer would know how to write the code. So in the analysis model, it's purely logical. That is, it's purely business logic, without concern for any platform information. While in the design model, we need to consider the implementation environment. So when to transition from the analysis to design. So system is gradually structured into basic parts with well-defined relationships among them in two stages. So one is building the skeleton. That is, parts come together to produce a stable basis. Skeleton is provided by the software architecture. The other is growing the system. That is the process by which the parts aggregate around the skeleton to produce a final system structure accomplished by the analysis and design workflows. So this is really like when you are building a sculpture, you build the skeleton first and gradually add meat to the skeleton. So why not go straight to implementation from analysis without going through the design stage? So the reason is that we need to consider issues ignored in the analysis stage, like the non-functional requirements. That is performance, reliability, all the requirements related to how well the system performs, and implementation environment. So both are ignored in the analysis. And another reason is that an analysis model is not sufficiently formal. That is, it often relies on natural language to describe what each actor, each class does. So now we need to make it more formal in computer language. So we need to refine the classes. Perhaps in the analysis model, you only have a natural language description of its role. Now you will refine it into more concrete operations with the signatures and in terms of a formal syntax. Determine which operations are needed and determine how classes should communicate. Well, in the analysis model, perhaps you draw a line that says Class A communicates with Class B. There's a dependency relationship. But now you actually specify how they communicate. Is it by procedure calls, is it by message passing or shared data? So it should be very more specific as to the communication mechanisms. So we also want to validate the analysis results. how well do the analysis model and requirements model describe the system? What is not yet clear? So, in the process of doing the design, you often run into ambiguity points. And this is because of the inherent informal nature of the analysis and requirements models. You need to formalize and make more precise parts of the system. So this is really serves as a validation of the analysis model. So design, you need to decide how system design goals will be realized. So goals come mainly from non-functional requirements, system qualities that we're trying to optimize. There are many goals, many desirable system qualities. We actually discussed this way back early in the course, in the introduction chapter. So you have, say, performance qualities, response time, throughput, memory consumption, dependability, maintenance. Is it easy to maintain, to extend? If you add a new module, do you have to modify many other modules? Say portability is when if you move from Windows to Unix, how hard is it to do the porting? And say readability, if you're bringing a new guy into the development team, how long does it take for him to understand the source code? So say cost, including development cost and deployment cost. Is your software so fast and slow that you need a very fast processor, or is your software so efficient that you only need a cheap processor? So that's deployment cost. Administration cost. Is your system very easy to use so that the user can really use it himself? Well, or is your system so complex that you need dedicated IT staff to help you do the administration? And maintenance, that is new upgrades to the system, download the software patch, etc. So all these represent costs. So all the others, I will not go into details. So all these are desirable system qualities. In an ideal world, you want all of them, right? You want it to be fast, to be cheap, to be robust, to be modifiable, to be portable, everything. But that's not realistic. So you need to make decisions. Choose appropriate design goals for your particular application. Design goals guide the decisions made by the developers, especially when implementation trade-offs are needed. Perhaps one implementation is very fast and efficient, but is less robust and less reliable. The other implementation is slow but very reliable. So depending on which one is more important to you, you should make different design decisions. So usually only a small subset of the design goals can be effectively realized simultaneously. As I discussed very early, so if you're designing a aircraft control system for a Boeing airplane, then reliability is of utmost importance, and the cost and time to market are not that important. But if you're developing a mobile game for a cell phone, then cost and time to market are the most important, while reliability are less important. So what if it crashes once in a while? So therefore, we need to prioritize the design goals and possibly develop trade-offs against each other as well as against managerial goals, including a schedule and budget. So, as I said, delivery time versus reliability for different applications, and space versus speed. So, this is a classic computer science trade-off of space versus speed. If you have more memory space, you can have faster software. If you have limited space, perhaps you need to use a more time-consuming algorithm. So that's design goals. Now, implementation environment. So at this design stage, we need to consider the technical and managerial constraints under which the system should be built. Technical meaning that so you're designing a game for a cell phone. So a cell phone cannot use a Pentium. It uses a slower, cheaper processor because the Pentium is too expensive and too power consuming. So you need to consider that constraint when you're designing your software. It shouldn't be too overly complex. And managerial constraints refer to cost and budget. So what hardware software will the system run on? Hardware limitations. Hardware with their limitations. So if you're developing workstation scientific computing software that runs on a supercomputer versus a mobile game software that runs on a cell phone, you have different limitations of the hardware. Distribution. So will your system be a centralized system or a distributed system? Or system software, is it running on Linux or Windows? So what programming languages will you use? OO or non-OO? So perhaps OO is easier for the developers, but object-oriented languages have more overhead. Perhaps if you have a very performance-critical application, you need to use C, non-OO language. And memory management. So that is if you use Java with this automatic memory management, where you only allocate memory and rely on the garbage collector to free the memory for you, then you never have memory leaks, right? But that comes at the cost of performance. So you need to consider the trade-offs. So what existing software do we need to use? That is third-party software. So you're developing the registration system software, but you're not developing the whole thing from scratch. That will take many, many years. Instead, you're buying some software from third parties, like DBMS. In our case, it's Microsoft Access. And UI development toolkits. We have the Microsoft toolkits for the dialog box development. Network facilities, we have TCP/IP built in to the operating system and legacy systems. So perhaps you can reuse part of the legacy system so that you don't have to develop duplicate the functionality. So what development organization, people and organizations will be involved? That is distributed development. This is especially important in the age of globalization, where you often have distributed teams. One team in the US, one in India, one in China. How do they collaborate to finish a single piece of software? So you need to have clearly defined interfaces between the different modules assigned to different teams. And team competencies, that is, you need to consider what skill sets do the developers have. If none of the developers know Java, and then you decide to adopt Java, then perhaps it's a risky decision. So general strategy for technical issues are encapsulate and isolate the implementation environment. So here's we create bridge classes that represent occurrences of components in the implementation environment. So here's the collection of application system classes in green that require file access. So here are 3 different operating systems: Windows, Unix, and Mac operating system. Now, if you want your application software to be portable, but you cannot encode the OS system calls directly into your application system classes. If you say, if you're calling, say, Windows API within the application class, then when you move to Unix, perhaps you need to search and replace many places of system calls, OS calls. So the solution is to have a bridge class called File Manager that encapsulates all the calls to the OS. So that the application classes see a unified interface. Say, application class only calls open file. You don't care what OS it runs on. Underneath, in the File Manager, perhaps you have one version of File Manager for Windows, where the open file actually calls the Windows API within its method implementation, and another version for Unix, while the open file calls the Unix API. So therefore, you create encapsulation so that if you move from Windows to Unix, you only need to modify the File Manager. You don't have to modify anything related to the application. So this is good because in File Manager, you only need to perhaps change a few dozen places, while in the application, there are perhaps hundreds of thousands of places where you call a file operation. So changing the File Manager is a lot easier than changing the application. So we often need to define many additional classes to deal with the implementation environment. So File Manager is one example. Of course, TCP/IP networking database. You can all imagine designing the bridge classes that sits in the middle between the application and OS to encapsulate the platform differences, so that makes it easier to port your application. Okay, I think we'll stop here. So see you next time.